So you have this cylinder of mass m, and you can assume that it's rolling without slipping. That's given. And there's a rope that's wrapped around the cylinder, and you're pulling on the rope with a 50 Newton force. And you have to find the force of friction, and you also have to find the acceleration of the center of mass of the cylinder. So you have to find the acceleration of the center of mass of the cylinder. So when I say acceleration of the cylinder, I really mean the acceleration of the center of mass of the cylinder. Okay, so how do we do this problem? What we can do is, we know, as our big discussion that we just had, there is a force of friction. Now, in this problem, it would be hard to forget the force of friction because it's one of the things we are asked to calculate. But I could have asked this problem as, I could have not mentioned the force of friction. I could have just said, calculate the acceleration of the center of mass of the cylinder. That is when students completely forget about the force of friction, right? But in this, so the wording of the problem is such that we can't forget the force of friction. So it's one of the things we have to calculate. So there is a force of friction. Now, if it's rolling without slipping, what kind of friction is it? Is it static or kinetic friction? All right, so if we could change the setting of responses to fast, that would be really appreciated. Okay, so the default is slow, but if we could just temporarily change it to fast. Yeah, thank you. Static friction, very good. All right, so now static friction, we know the direction is not very clear. It could either be to the right or to the left. If it was kinetic friction, there would be no question about that. Now, for this problem, can you guess what the direction of friction is? Do you think it's going to be to the right or to the left? Static friction?
I think to left.
Okay, the correct answer is it's actually going to be to the right, right? Okay, so let's, as I told you, as I promised you, you don't ever have to figure it out intuitively. You don't have to spend any brain power to figure it out. So you can just make a guess about the direction of the friction when you're setting up the equations, and the math will tell you in the end whether your guess was correct or not. So what we're going to make a guess, and we are just going to guess that the direction of friction is to the right. Okay, and this is a complete guess at this point, right? Okay. So let's set up the equations right now. So we know that there are two forces. I'll just keep this as capital F rather than the numerical value. So I've got two forces acting on the system, and I want to find one of the forces is unknown, and I want to find the acceleration of the center of mass of the system, right? All right, so what we're going to do is we're going to set up Newton's second law the same way we've been setting it up since chapter 4 and 5. And if necessary, we'll also set up net torque equals I alpha, right? All right, so we'll start with F net equals mass times acceleration. Now we're done with all the intermediate steps. We've identified the system, we've identified the forces. Sign convention could be right is positive. And actually, since we know that we're going to need to set up Newton's second law in angular form as well, let's also set up our rotational sign convention. So if we choose right is positive, then what rotational sign convention do we need? Counterclockwise is positive or clockwise is positive, do you think?
Clockwise is positive?
Yes, because when the wheel moves to the right, it rotates clockwise, right? So if you choose right is positive, you have to choose clockwise is positive. So these are our signs. All right. So let's set up F net equals mass times acceleration. Can somebody help me set up the F net part? It's nothing new about that at all. In symbols like F and capital F. So what do I get for the F net part?
I think it's big F plus little f.
Exactly. Big F plus little f, that's it, is equal to mass times the acceleration of the center of mass of the system. That's what we get from Newton's second law, right? Now, this equation is not enough because there are two unknowns in the problem, the friction and also the acceleration of the center of mass. So both of those are unknowns. So unfortunately, this equation will not be enough. We will need one more equation to solve for two unknowns, right? That second equation will come from net torque equals I alpha. Net torque equals I alpha. All right. So now we have to find torques. Okay, so let's start with the torque. So net torque means the torque of everything. Now, what are the forces acting on the cylinder? There is F and there is little f. Any other forces acting on the cylinder? Can you think of any other forces that are acting on the cylinder? Maybe along the y direction?
If we count gravity.
Yes, there is gravity, which is acting downwards like this. And anything else? Yes, Seung, what were you going to say?
Normal force.
Yes, very good, the normal force. Now, when I'm doing net torque, will gravity and normal force, do they have any torque about the axis of rotation of the cylinder? We discussed this yesterday.
No,
No. Why not?
because they both go through the
Yes, very good.
reference point.
Excellent. That's exactly correct. So they both go through the reference point, which is the center of the cylinder. So they pass through the reference point. So there is no, they have zero lever arms. So they don't have any torques. So let me just get rid of them. Actually, I'll just keep them, but there's no torque due to Fn and mg. So when you're doing net torque, you do have to take the torques of all the forces into account. So I'm just showing you that I haven't forgotten about Fn and mg. They just simply don't have any torque, so they're not going to show up in my equation. All right, so let's move on to finding the torque due to capital F. Is capital F going to, is it exerting a clockwise or a counterclockwise torque on the wheel about its center? So let's figure out the direction first. Is capital F exerting a clockwise or a counterclockwise torque? Yes, capital F is trying to rotate the system in the clockwise direction. By itself, it's trying to rotate the system in the clockwise direction. Is everybody clear about that? Ian, is that clear? Okay, very good. So the torque due to capital F is going to be clockwise, so it will get a positive sign in my sign convention. Now let's write down the magnitude of the torque. Let's take the radius of the wheel to be r. We're just going to do the whole thing in symbols. So instead of the 15 centimeter, we'll just take the radius to be r. So what is the torque of F going to be? So we did similar things yesterday. What is the torque of F about the center?
FR.
Yes, F times R. Very good. All right. So plus FR is the torque due to F. So we are done with finding the torque due to F. Now we just need to find the torque due to little f. Is little f exerting a clockwise or a counterclockwise torque about the center? What do you think? Bryce, what do you think? Is little f exerting a clockwise or a counterclockwise torque? All right, so anyone? Oh, Bryce replied on the chat. Yeah, it's exerting a counterclockwise torque. Very good. And so it's going to get a minus sign. And what is the magnitude of this torque going to be? What's the magnitude of the torque due to little f going to be? Ava, what do you think it's going to be?
Would it just be little fr?
Yes, very good. Little f times r. Excellent. Everybody clear about the net torque? So there are only two forces that have torques. That's the capital F and the little f. Fn and mg don't have any torques, so that's it. When I do net torque, this is all that I get. And I've taken the signs of the torques into account according to my sign convention. And so that is equal to I times alpha. Now this is a cylinder, right? And it's rotating about its own axis. Does anybody remember what is the moment of inertia of a cylinder about its axis? It's in the table, but does anybody remember off the top of your heads?
Is it 1/2 mr squared?
Very good, 1/2 mr square times alpha, right? So I have found two equations connecting my two unknowns. Actually, I have found an equation. The second equation doesn't have the ACM, but we do know that it's rolling without slipping, right? So when it's rolling without slipping, a very important equation that applies is VCM equals R omega. And that together with that, we get its cousin, which is ACM equals R alpha. These two come together. So so I can use this equation right here to get rid of the alpha, right? So my second equation becomes FR minus little fr is equal to 1/2 m r square. Instead of alpha, I'm going to use ACM divided by R. I could only do this because it's rolling without slipping. If I didn't know whether it's slipping or not, then I wouldn't be able to proceed any further. Like this step came from the fact that it's rolling without slipping, right? All right, so I can clean this equation up a little bit. I can probably divide both sides by R, and that gives me capital F minus little f is equal to, all the R's cancel out, 1/2 m ACM. So I got two equations. This is my equation number 1, and this is my equation number 2. Both of them came from Newton's second law, right? All right, so now it's just a matter of solving these two equations for the two unknowns. So it's just a matter of algebra, and I'll just do that. Maybe I'll just do that on a Word document because I'm running out of space here. So the two equations that I got were F plus little f is equal to m ACM. And the second one that I got was F minus little f is equal to 1/2 m ACM. This is just algebra from this point on, like the physics part of this problem is done. So I just need to solve these equations to get little f and ACM. These are my two unknowns. All right, so what's the easiest way to solve them? Well, I noticed that there is a plus f in the first equation and a minus f in the second equation. That suggests that if I just add up these equations, then the f's will just cancel out. So let's try that. So this is called the method of elimination. So 2f is equal to 3/2 m ACM, right? And so from here, I can immediately solve for ACM. So f is gone. I can immediately solve for ACM. ACM is going to be 4f divided by 3m. That's one of the answers. So ACM is going to be 4f divided by 3m. Okay. All right. Yeah, so a numerical value for m should have been provided, which I forgot, but you would need a numerical value for m. You have a numerical value for f. All right. Now, what about the friction? So I can plug this ACM that I just got into any of these, the two equations and get the value for friction. So if I do that for the first equation, F plus friction is equal to m. And for ACM, I'm plugging in 4f divided by 3m, right? And now I can just solve for the friction. The m cancels out. And so I get little f is equal to 4f divided by 3 minus capital F. And so that gives me f divided by 3. That's the answer. So that's the magnitude of the friction, right? It's 1/3 of little f. Now, recall that when I set up these equations, I made a guess for the direction of the friction, right? I just randomly assumed that it's to the right. How do I know that whether that guess was correct or not? The answer that I got for friction seems positive. I mean, it's a positive quantity because f is positive. So the friction is f over 3. So that's a positive quantity. If I get a positive answer in the end, that means my guess was correct. So positive answer for f, positive f means that good guess. The guess was correct. So I don't need to change the direction of friction. Suppose I had incorrectly guessed the direction of the friction, then what would have happened is in the end, I would get a negative answer for friction. And that is simply the math telling me that my guess for friction was wrong. The direction of friction was wrong. I simply need to point my friction arrow in the opposite direction. So the only thing that I would need to do is change the arrow for the friction and make it point in the opposite direction. That makes sense? So I told you that the math tells you in the end whether the friction, you guess the correct direction for friction or not. And so you can use that, and you don't need to actually expend any brain power in figuring out the direction of friction. So is everybody clear about this problem? All right, now as an exercise, here is what I highly recommend doing. So I made a guess for the direction of friction here. And I went with the guess that I went with was the correct direction of friction. So here is what I want you to do. Assume that the friction points to the left. So made the wrong guess, then friction would point in this direction if you made the wrong guess, right? So then I want you to set up the same equations that I just did. Newton's second law in the horizontal direction, and also net torque equals I alpha. Your equations will be a little bit different because now your friction is pointing in the opposite direction. Work through the algebra just like I did. It's practically going to be the same thing, just a few things will be a little bit different. And then in the end, you will find that you have exactly the same magnitude for friction over 3, but you get a negative f over 3 if you do that, right? And that is the negative sign is basically just telling you that your initial assumption about the direction of friction was incorrect. That makes sense? So do this problem the other way as well, right? With the wrong guess for the direction of friction, and check that the math actually tells you that your guess was wrong.